Welcome, welcome. Today we're going to be talking about the nature of science. So you should be following along in your notes. And today's lesson is mainly about how scientists think and why science is structured the way that it is. Alrighty. So our first question is why science? So my question to you all is, does anyone recognize this image? Maybe not of Homer, right? That's Homer Simpson, but particularly the image that this is supposed to be conveying. Does anyone recognize that? All right, so you might not be familiar with it initially, but I'm going to quickly share a Google search. And this is actually, we're going to head right over here and we're going to type in Vitruvian Man. All right, so this is the Vitruvian Man's image. This is a famous drawing by Leonardo da Vinci, and it is one of anatomical proportions. So this is the image that he is originally showing. He's showing the inside of the leg, front of the leg, side view. He's trying to show all the body proportions in their perfect proportions, and he's even making notes with the circle and the square that you can see there as far as how it should be laid out, how the human body is generally proportioned. So it took lots of study for him to notice this, and definitely lots of measurements for him to be able to circumscribe it within a circle and a square. And so that means that he had to do research, take data, record, and then compare. He did science there, and that's something that we're going to be practicing throughout this course. So as you can see, there's definitely a strong reference to that Vitruvian Man in this image, except for now they've just kind of replaced it with Homer's image. Alrighty. So when you see things in the world and you've got a question about them, sometimes you can ask a question that you can go back and test for. So these are generally going to be called hypotheses, or to make a hypothesis, or to hypothesize. Right, so those are just multiple ways to say it, but scientists hypothesize in order to try to explain what they think will happen in a certain situation. So what that means is that you're going to see something happen, you're going to make an observation, and you're going to think to yourself, well, if I were to repeat that in a very organized and manageable fashion, I think that I would get this kind of result. And so long as you structure that question correctly, you can easily test it and then come back and compare to see if you're correct. So anytime you make a prediction, you are coming really close to a hypothesis, all right? And then there's this note here that says long held assumptions should be questions, and should is in italics. So the reason that that's stated is because the bad thing about assumptions is that they will have a tendency to make you go with the flow of just what everyone else is suggesting is true. And unless you actually investigate it for yourself, do research and test it, you may be just following in line where you could be in the front of the line, leading the way into a new understanding in this particular topic. All right, so a lot of these frontiers have been very well explored in science by now. But just to give you an example, one of the things that was a long-held assumption in ancient Greece and in ancient Rome was that every time that the thunderheads built up, got loud, and started raining down lightning upon the ground, it was the thought that Zeus was either angered or was in some kind of a battle, or if we're talking about Rome, Jupiter, whatever their lightning god was for that time, they believed that the lightning god was angry with them either because they hadn't prayed correctly or they hadn't done the right sacrifices, or that the god was trying to fight some kind of a monster, maybe the Titans. And so it was believed that if your house got struck by lightning and caught fire, it was fated to be so, because that might have been the site where some ancient evil spirit that Zeus was trying to keep down was trying to arise. So this was the long-held assumption that they held for many thousands of years. So we fast forwarded just a little bit to a guy you guys know of named Ben Franklin. I'm going to tell you right now, he didn't invent electricity. He didn't discover it. That was well in the past, and we'll discuss that later. But one of the things he did do was he discovered that lightning bolts conduct electricity. That was one of the biggest things that he discovered, and that metal accepts that charge. So that idea of tying a kite to the string, or excuse me, tying a key to a kite string and then flying it in a thunderstorm and watching that attract lightning bolts let him know that that metal conducts electricity. So just that little discovery, that was a long-held assumption that he might have been scared that he was going to incur the wrath of Jupiter if he was holding to that long-held assumption of ancient Greece. And by questioning it and by testing that, he actually discovered a really important property about electricity and metal, and eventually led to the modern era that we see today. That idea of conductivity leads to all the wires for the devices that are currently bringing you this message. And so without that test, without multiple people like him throughout the ages that were curious enough to take something that everyone assumed to be true and to put it to the test, to rigorously, methodically take data on it and then communicate those results, we would not be where we are today. So that's why it's a really important idea to question long-held assumptions. So, how do you succeed? How do you achieve success in science? You be creative and you think outside of the box. So this is one of the things that I encourage in class and just in life. If you're running into an obstacle, sometimes just thinking around the problem, coming at it from a different angle, or thinking about it from a different point of view can give you all of the perspective that you need to fix the problem or to get over that obstacle. So those creative experiments end up being the best ones. Things that were accidents oftentimes end up being really important scientific truths later down the road, which is why recording what happens is so important. In case something does happen, you can repeat that accident on purpose the next time. All right, and the next thing is you're going to persevere. This is something I encourage in this class, and again, something I encourage in life. You've heard me say this before. If at first you don't succeed, try again. That means you need to be constantly trying to get it correct. All right, so right here, you're going to think creatively and then think outside of the box, and those creative experiments are the best ones. So you don't get to be creative if you give up. Oftentimes, creative people are the ones that sit with adversity and struggle, and they sit with that obstacle and they chew on it. And they try to figure out a way around it, and it's spending time with that difficulty that ends up giving them the creative or new perspective that they needed to get past that block. And that perseverance is really what gets them there. All right, so if you did succeed, so like if you don't succeed, try again. And if you did succeed, do it again and make sure it was correct in the first place. So if you finished your test early, I'd hope that you go back in general in person and check over your answers. All right, because sometimes haste makes waste. And what that means is that if you're being too hasty, too quick, you might make a mistake and never notice it because you're just so bent on trying to finish that task or that item. So make sure that you're always ensuring that you did it right and that it wasn't a fluke, it wasn't an accident, that it's replicable. And then keep going if you didn't succeed. Try it again. Try something different. You guys have all heard the story about how Edison, hopefully, found 999 ways not to make a light bulb. And what that means is that he and his large team of scientists that did most of the work for him, he was largely the money behind it and the initial name on it. He assigned them, try these different things, try different materials, try different kinds of glass. And it wasn't until they finally found the one that worked that they knew that they could stop failing. They failed way more than they ever succeeded, but that success, again, brings us the lights that light your home today. All righty. And the next one is going to be to question everything but make your questions meaningful. So why do you want your questions to be meaningful? Because otherwise it's a waste of breath and it's a waste of thought. So you can ask really meaningful questions, but that generally means you have to think about them before you ask them. It can't just be the first question that pops to your brain, because oftentimes there's a deeper, more specific, and better, more meaningful question hiding just below that initial question you ask. And it just takes a little bit of time with that thought in order to get there. All right. And so by meaningful, what that really means in science is that you can create an experiment based on that question. So I'm going to give you a question, or I'm going to give you a scenario, and you will have thought of this question, hopefully. So most people have been in a home, maybe it's their house or another building, where you have either opened a window, opened a door, or closed a door, and this caused something else in the house, another door, maybe the blinds in your room, or really anything, to suddenly move. All you did was close a door or open a door, and then suddenly down the hallway, the door opened or the door closed in response to what you did. So I'm sure that everyone's experienced that at least once, and if you haven't, just kind of follow along. Your initial question was, who did that? Is that a meaningful question here? What if you're in the house alone, right? Your first thought is, oh no, there's a burglar, right? So who did that might be your first question, but that's not an experiment, right? A lot of people immediately go to ghosts, and so that's a really good point. And this is actually something that's built into the human brain. Most things that happen without reason happen because a person did them, and you just don't know their reason, right? You probably found something to go, what the heck is this? Why is this like this? And so when something happens that you don't have an explanation for, your brain defaults to something that's called cause of agency. All right. An agent is a person that does something. And so the cause of agency, when you don't know, your brain goes, who did it? Right. And so this is actually where paranormal activity and ghosts end up getting their root. That's their foundation in the human psyche, is just things that go bump in the night. It's a noise. It's a sound or a small movement that didn't make sense because you think it moved. Something or someone moved it, and it wasn't me. It must be a ghost. And so this is where science starts to cut through superstition. And I use this example because most people at first immediately think either someone's in the house with me or there's a ghost. Oh no, run. And the reason that I picked this example is because if you do science, if you start actually following an experiment, testing it, and recording your results, you will quickly prove that not only is there not a ghost, that you have really, really good insulation in your house. All right. And so let me talk about what that means. So you're going to observe and come up with a question. So when I close my door, it closes the door down the hallway. Okay, so that's my observation. What's my question is, why did the door down the hallway close when I closed my door? Okay, so maybe you say why, or maybe you can specify that and say, what happens to the door down the hallway when I close my door? This is a more open-ended question. When you say why, then you're looking for a cause and it's really pointed. But if you say what happens, then it's just observations. Then you can do a test. You can, okay, I close my door and I'm going to pay attention to what happens to that other door. All right. Then you're going to ask questions as you see that. Okay, so you closed your door, and every single time you noticed that the door down the hallway that's open closed. If all the rest of the doors were closed. Okay, so maybe you've got multiple doors in your hallway, and if they're all open, nothing happens. But if every door but the bathroom door, whichever door we're talking about, closes, then you're going to notice that there's a relationship between your door closing and the door down the hallway closing, and it's not a ghost, unless the ghost is just really in sync with you. So you're going to do that research. You're going to look into that. And at this point, you might even Google it, right? So some people would have this opportunity and say, well, I'm just going to look it up. We're going to figure it out. All right, and that research is going to suggest that you might want to look into pressure. All right, you start looking into pressure. So you're going to form a hypothesis. You're going to say, if I close my door, then I expect the doorway down the hallway to close if every other door in the hallway is closed. And then you have done this based on you testing, you closing and opening doors and trying to see what's happening. All righty. Then you're going to test that hypothesis. All right. You're going to test that hypothesis and repeat it, and you're going to perform that experiment in order to try to take data. You're going to record, okay, so you might just have a checkbox, open door, closed door, whatever that might be. You're going to have some kind of way to record your findings. You might just write it down. Trial 1, opened door down the hallway, didn't do anything. Trial 2, closed door down the hallway, closed. So we've now set up two things that we're looking at. We're looking at something that you're controlling in the experiment. You said, if I do something, then I expect this other thing to happen. All right, so what are you doing in this experiment? So what are you controlling? What are you actually changing physically in this experiment that I've given you the example of? Anybody?
The doors that are closed.
All right, so the thing that you're changing is your bedroom door, right? You're closing one door. And so that's what you're controlling. And then you're trying to see whether the other door opening or closing is dependent on what you just changed. So let's put that in terms of what we're looking at here on the slide. So the independent variable means it's independent of change, meaning you're the one that has to change it. It's not going to change on its own. All right. And so the factor you change on purpose. This is what you are controlling. Okay. This is the knob that you have that you're twisting. Maybe it's temperature. All right. Now they give you two examples here. Maybe it's the size of your engine or the amount of fertilizer on plants. So we're going to see. So here you would be testing the speed of your car with the size of the engine. And then in the red, the amount of fertilizer on plants is going to be the growth rate of your plants. That's what you're testing. All right. And in our example, you closing the door is going to be what you change. There can only be one independent variable. That you can only be changing one, or else then you're not getting accurate scientific data. So then you have a dependent variable, and that dependent variable results will vary based on what you've changed. So what that means is that the result of what you changed is dependent on what you changed, right? If it's the result, then something had to be the cause, right? Cause and result, or cause and effect. So if the independent variable is like a cause, then the dependent variable is the effect, and it's what you're studying. This is what you're taking data on. So in the example of the size of the engine, you're going to change the size of the engine in order to determine whether that changes the speed of the car. All right, and as long as that car is not a tank, you are probably going to be pretty good to see a relationship there. And then the amount of fertilizer on plants, you want to see whether that affects how fast those plants grow. And so the growth rate of the plant depends on how much fertilizer you put on those plants. So within the experiment, you've got constants. These are things that you're going to hold constant. You're going to make sure that they don't change so that all of your variables are not fighting each other. So factors are variables that you try to keep the same to make the comparison fair. So in the example of, for instance, the engine in the car, you've got test the speed of the car on the same track with the same car. So what you're going to be doing is the only thing you're changing is the engine inside the car. You're not going to change the wheels. You're not going to change the track or the car, because then you're going to have different results. And that's going to make this is exactly the scientific method. We're currently talking about the scientific method. You want to keep everything the same so that you can say that it was the engine and it wasn't anything else. All right, so same amount of water and light on plants. So you don't want to water one of them more and put more fertilizer on them, because then you're changing two things. So you want to hold the water and the light constant so that you can make sure that it's the fertilizer that matters. And so in the example of the doors in the hallway, maybe you want to close all the doors. Make sure that it's just those two doors that are interacting. You're going to keep every other door closed. You're going to make sure nobody's coming in and out. You're going to keep you're going to open the door the same speed. You're not going to like slam it one time and barely close it another. You're just going to test to see whether opening your door or closing your door affects that door down the hallway. So within the experiment, you've got two kinds of groups, all right? You've got a control group and an experimental group. So an experiment is the one group that receives no treatment. This group is used for comparison. All right. So the speed of a car that did not get a larger engine, you're going to need a baseline to compare to. So you would probably put in a different engine of the exact same size just to prove that it's the size of the engine, not just the original engine that you had. This just makes sure everything's good to go. So the growth rate of plant that did not get any fertilizer. All right. So if you're using differing amounts of fertilizer, right, you're going to have one plant that didn't get any fertilizer, because what if the fertilizer isn't doing anything at all? How would you know if you didn't compare it to something that had none? So that's one way to test. All right, now the experimental group is the group that has had the independent variable added to it. All right, so you're going to take the group that you're actually changing, and this is what you're experimenting with, and so it is your experimental group. So the example will be the car with the bigger engine, the growth rate of a plant that did receive fertilizer. So this is the group that you're actually changing things for. You're actually taking the time to change one variable and measure the result in your dependent variable. So we're moving along pretty good. All right. Now we're going to look at why scientists repeat data, why you're going to repeat your trials, why you're going to take multiple forms or multiple sets of data. So scientists always, look at the fact that that's completely capitalized, always confirm results. So repeated trials, you're going to repeat the experiment to increase confidence in your results. The average of the results to reduce random error, take outliers into account. More data equals better results. So let me pick this apart. Okay, so you try anything and you get a certain result. You want to continue to try that same thing to make sure it wasn't just an accident the first time. You also want to make sure that you're doing it correctly every single time to try to produce the same results, and you will get more and more accurate data. All right, if you only took one shot from a three-point line, if we're talking about basketball, and you miss, are you going to tell yourself that it is impossible for you to make that shot because you missed just once? What are you going to have to do to try to convince yourself you can either do it or you can't? You're going to have to take multiple shots. And in the same way, you have to take multiple sets of data so that you can prove that the first time wasn't just an accident. You can prove that what you think you see in the first trial is true and that it shows up in other trials, and then it becomes a truth. You average the results to reduce random error. All right, so let's just say, you made that three-point shot 6 out of 8 times. All right, so the 2 where you missed would technically be random error. I mean, you're on average 3/4 of the time you're going to make that shot. All right, but if you don't average it, you won't really have a percentage of what to expect. Now, outliers would be like if one of the times you decided to run to the other end of the court and just kick it, right? You didn't throw it, you're not actually trying anything, and it made it, right? You didn't expect it, nobody expected it, it's way out of the possibility. You wouldn't want to count that because that's not normal circumstances. I will show you data with outliers in it later, and this will make more sense. This is data that's way off to the side, all right? So if your main data set, you guys know what a ruler looks like, right? So if this is my data set, and if I plotted a line through the data, it looks like that. And then I've got a piece of data way over here, over to the right or to the left for you guys, then that means it was probably an accident, and you can throw that out or else it's going to throw off all your data. The more data you have, the better, because it ends up making the average more accurate. Gathering data, more data equals better results. So does anyone know what the middle school rule for data is? How many data sets do you need? Minimum.
2.
Not quite. We're close.
5.
A little bit too much. So generally what most science teachers who know that they're on a time crunch will tell you is 3 data sets. I need 3 pieces of data. All right? Because when you have 2, the average of 2 is still not accurate. You need a third to be a tiebreaker. All right? You always want an odd number of data sets so that there's a tiebreaker. And 5 is actually generally what I suggest, 5 to 10, depending on the scenario. So if I have you take data, I'm going to suggest 5. But in middle school, generally, they're going to be suggesting 3. And then when you get to college, you're probably looking at somewhere closer to 13 to 17 pieces of data. All right, so they almost triple the amount that they want because they want better results. They want you to prove that you really know what you're doing. All right, so you want at the very, very bare minimum 3 results, but 5 is really preferred in my class. So there we go. Evidence/data. Your data is evidence. Evidence is what you observe, not what you think is happening. I want you to realize that because you make a hypothesis, you then have skin in the game, so to speak. You think this is going to happen, and so your evidence cannot be affected by what you think. It has to be affected by what you observe and record. So even if you really hope this one thing, like you really want to be able to fly, and so you keep testing it, and because you think you can fly, that doesn't mean you have evidence that you can fly. Because every time you try that, I promise you, your data is going to suggest that you can't fly. And so the evidence is that humans can't fly. All right? So evidence can be measured and observed using one's senses. All right? I think this. I can't observe that. That's your thought. I can't measure your thought. All right? So what you've got to remember is that data is where the evidence comes from. So if you're looking for evidence of something, you got to take data in order to prove it, right? If you want to prove that this thing happened, or you want to prove that this will be the way a certain chemical reaction plays out, you got to take data and then show that it consistently is the case. That means you got to be observant. You cannot be a half awake, barely paying attention kind of observer, because you're going to miss something. You will miss something, and it will come up in the data. Look how many slides there are about data. It must be really important. So you've got 2 main kinds of data, and you should have heard these before, but you will hear them plenty from now on. You've got quantitative data, which means that results can be measured and described with numbers. All right, quantify. All right, that means to have numbers. You have a number associated with quantitative. All right, the examples they gave you are growth rate, speed, so those are the 2 they mentioned with the engine and the fertilizer, length, height, mass, volume. If you can put a number on it, you can have quantitative data with it. Now, qualitative data is results that are described in words, not numbers. So these are results of the 5 senses. All right, so your example will be color, texture, looks healthier, feels softer, it smells burnt. So, oh man, spilled some water. So these things are things that you are going to use your senses and not numbers to measure. So just be aware of that. All right, let me just get the electronics away from the water real quick. Okay, keep lids closed. All righty. So qualitative things are things you're measuring with your senses. Quantitative data is data that you have measured and have numbers for. And then you make a conclusion. You have to take everything you've done and you have to restate your hypothesis and state whether you supported or rejected it with your data. All right, so I thought that if I close my door, then the door down the hallway would close. I did this 10 times and found that every time I closed my door, the door down the hallway closed. Thus, there's a relationship between the 2. That would be a conclusion. All right, supported or rejected. And then right here, sharing what has been learned. So you're going to communicate your data with your colleagues by publishing it in journals. All right, so this is where, one second. I got to pause the recording. I've got water dripping onto an outlet. So you're going to communicate that data with your colleagues, which means you're going to take that data, your conclusion, your hypothesis, you're going to put it all together and put it out there for people to test. You're going to record everything you did carefully so that they can go back and do it themselves and check to see whether what you're saying is true. Make sure you didn't make any accidents. Maybe it's your equipment. Maybe it's the way you looked at it. Science is always tested. Always tested. Once a scientific idea becomes widely accepted, it will continue to be tested and experimented on. You guys will be testing scientific truths all the time in this class. That's because we want to test to make sure they didn't suddenly change. And then we have to do something about that. So just be aware that we're always going to be testing, and then every time an experiment is run, new information is learned. So you can never learn too much information.